gonna skip over it.
Do
Everybody
you
knows
plan
how-
on that, the projects like going with the sections that we're doing?
Yes, yeah, so I feel good about that, I feel like we covered it pretty good. Everybody knows how an electron is produced. What about space charge effect? I don't know if that's later on in the section, or maybe in image production. It probably is in image production because we're talking specifically about safety. But just in case it's not, who knows what the space charge effect is? Cloud of free electrons. So it's the limitation of how much thermionic emission can occur. So the space charge is, say you set a technique to be 50 mass. Only 50 electrons can boil off. That's the number. It sets the quantity for space charge. And it has to do with thermionic emission. So we have thermionic emission, the boiling off of electrons, and then we have the space charge effect, which limits the actual electrons. Yes?
In my home study for guy says that one of the questions that's really repeated on the board exam is where the current that produces thermodynamic emission comes from.
Where does the current come
Yeah.
from?
Separate direct
It's coming
current.
from step down transformer.
Oh, step down transformer. Well, we'll talk about with production. So we'll go over that in X-ray production. What do you need to actually have electrons being produced? Step down transformer, step up transformer. You actually need both of them. Good. What did he say specifically?
So the question will be, where does the current that produces thermodynamic emission comes from?
Step down transformer. Okay. All right, so we'll talk about that in production under actual image production, not safety though. So target interactions, how do we feel about these? Are we good about them now? Feeling good? Okay, so we talked about brims and characteristics. Remember, these are gonna be occurring in the actual tube, so within the target. All right, let's talk about the X-ray beam. So frequency and wavelength, and then beam characteristics. So what do we have for X-ray beam, frequency and wavelength? We know that they're how related? Inversely related, or they share an indirect relationship. So if one goes up, the other must go down. Do we know what frequency and wavelength is?
Yes.
You wanna talk about it? Okay, frequency, so how frequently it is occurring. Wavelength, the distance of an equal point on each wave. So if you choose to measure from crest to crest, that's cool. If you choose to use trough to trough, that's either one. So successive points on the waves. You can't use a crest on one and a trough on the other. They have to stay consistent or successive. All right, what else do we have about X-ray beam, frequency, and wavelength? Anything else?
Frequency is in hertz.
Good. The measurement of it. Frequency is in hertz. So how much it is occurring is in the measurement of hertz. Good. I like it.
And with frequency, you can relate that to the oscillation.
Oscillation. Good. I like it. I like it. Okay. Questions about that? Anything else? How are you guys feeling? Good. All right. I'm trying to find my place here. Oh, okay. Okay. Here we go. Good. All right, let's go to the next section, beam characteristics. So we have quality, quantity, and primary versus remnant or exit radiation. So what do we have written down for quality?
Penetrating of the X-ray.
Good.
Penetration.
Penetration. Relative to KVP. Relative to KVP. So if you're going to make a chart, KVP versus mass. Oh, come on.
Increase in KVP is an increase in quality and increase in penetration.
I don't even want to touch this. Now I know why this was down. Sorry, Mia. Hold on just a second.
Is there a spray?
We're gonna have to scrub this board, huh? All right, so if we make two charts, we're done with the octet rule. Give me some terms that could describe these. So for KVP, we obviously know quality. So what about for mass? Quantity, good. All right, let's stick with KVP since we're learning about quality on this. What are our other terms that we could use?
Penetration.
Penetration, good.
What about filtration for that?
Filtration, I think that would be concerning dose. So I think if you were to pair that, I would probably pair it with mass, but it's not directly related. But it could be directed to dose specifically, because if you increase the filtration, you decrease those low energy X-ray photons, hardening the beam, making less dose. Contrast, good.
Two potential.
So we want to talk about something called subject contrast specifically. Subject contrast. So this is kind of a new term that they're bringing in. Subject contrast controls the KVP, or KVP controls the subject contrast, but not necessarily the post-processing contrast. What controls the post-processing contrast? Do we know? The software specifically,
Dynamic range
which is,
contrast.
you're so close. Lookup table, the lookup table. So if we're talking about not the actual beam and we're talking about post-processing, we're talking about post-processing contrast, the lookup table. Which we're gonna talk about it more in production, but just a brief. All right, anything else we wanna talk about? Quality, penetration, subject contrast,
How about, potential difference?
potential difference, I love it. Potential difference. If a potential difference does not exist, we have no voltage. Volts, anything else under this category? Quality, penetration, volts. How about energy? And then we could also say speed. Because remember, during production, we can affect the speed of the electron, not the speed of the actual X-ray photon. So quality under KVP, penetration, subject contrast, specifically what we're actually penetrating through, but not the actual contrast of the image, because we're going more digital, so they're finally changing our terms around a little bit, and we're associating more lookup table affecting the contrast of post-processing technique. Volts, potential difference, energy, or speed. Those are gonna be our quality terms. Anything else you guys have for those? Quality. Anything else under the section quality? All right. How about quantity? Quantity. So we know it's associated with mass. What is it? Number of photons. Number of photons, which means quantity, obviously. Current. Good. 2 current. And then let's also throw one more on there. Dose.
Patient dose?
Patient dose.
Current
Right.
would be with KVP, wouldn't it?
No, current would be with mass. Current would be with mass. Anything else we want to put under quantity or mass?
Rate of exposure?
Rate of exposure, good.
Intensity?
Intensity, good. Of exposure. Sorry, I'm writing sideways here.
Can you put like the measurement of it?
What do you mean?
It's like, I wrote down measured in MR or MGY.
Milliroentgen or milligray for mass? Ooh, for dose, yeah, we could put milligray here. What did somebody say over here, Mia?
Intensity?
Intensity of the beam, good. Intensity. Rate of exposure, and how about exposure time? Because we have milliamperage and we also have exposure time. So everything is all encompassing there under the mass section. Anything else we want to talk about there? Quality versus quantity. Quality versus quantity. I think we're good on them. I think they're good on moving forward. I like to draw the chart. If you have a mass or a KVP question on your exam, it might be wise to kind of write it out on your whiteboard. Go ahead and jot or dump the information. That way you can separate the two. So usually when you're test taking, especially with these board exams, these that are super long, and like she just said earlier, I wish you could take half and then come back and take another half of it. Normally what's going to happen when you're testing on the computer is once you read the question thoroughly, make sure you read the question thoroughly because they may throw a not in there or except, right? So you wanna make sure you actually know what it's asking you. But initially, after you read the question, when you're reading answer choices, the first thing that your mind goes to is usually what you're gonna read. So normally, the first thing you think of is the correct answer. However, read it thoroughly, right? But what I'm saying is don't read too far into the question, okay? They're not trying to trick you on this. They want to know if you know your stuff about x-rays specifically. So they're not going to try to trick you. Do they want you to know the information? Yes, especially regarding dose, radiation, safety, those kind of factors. But it's not gonna be a trick question. So if you're torn in between or you're thinking, I just don't know, there is an answer choice or a box where you can challenge a question now. So I just found out on this new registry, it's brand new for you guys. Don't spend every question, don't select challenge on every question, right? So they've been using some of these questions for years. Some of them are newer from the digital terms. But if you feel like there are just two answer choices and they're too close together, or the question just doesn't make sense, or there's not an answer choice, there is an actual checkbox where you can challenge the question and write a little sentence, right? Two answer choices or no answer choices. This is where kind of preliminary scores may end up changing. Now, I'm not saying they're gonna change every answer. And don't challenge every question on your exam. You may have less than 5 on your whole exam that you wanna challenge. I don't know if it's gonna actually increase your score and give you points. It's a brand new concept. But don't be alarmed when you see that and utilize it if you do think that two answers are very closely related. Okay?
Is that part of your time too?
It is part of your time. Yes, it is part of your time. So if you really feel like you're reading the question and there are two answers, or there's not an answer choice that is applicable at all, I would challenge it and write two answer choices. Don't write a paragraph, because you don't wanna waste your time, okay? All right, quantity and quality we feel good about. What about primary versus remnant? Primary versus remnant. What do you guys have written down for that?
Primary is also called useful radiation,
Good.
and it's the X-ray photons that are directed through the X-ray tube window and
Good.
into the patient.
And what about secondary, or, remnant or exit radiation?
That's what is used to make the image.
What is used to
That's
make
the
the
image
image?
forming beam.
The image forming beam, good. If you wanna distinguish these, primary is the useful beam, and remnant or exit radiation is the image forming beam, if you wanna separate these. I have a section in the Kettering book that says secondary radiation. They note it as radiation that is emitted from atoms of matter after an X-ray photon from the primary beam interacts with matter, also known as what? What would secondary radiation be? Good, characteristic, good. So that cascading effect to actually produce the image, characteristic radiation. And then I also have a note here on attenuation, so I don't know if that's in here. Oh, it's
Progressive
lower.
absorption.
Yes, absorption, so any kind of reduction of the beam. We talked about absorption and reduction of the beam as far as attenuation. So we'll come back to that. It's at the bottom of this section. Questions on primary versus remnant or exit radiation? Primary beam, useful beam, what we're actually producing. Okay. How about inverse square law? Adrienne covered that pretty good. Questions on it? An easy way to think of this, if you double your distance, you do what to your dose? Double your distance, you do what to your dose? Quarter it, okay? So I'm thinking on the registry, they're not gonna have some random 5-number question on there. They'll probably give you something like, you start out with an initial distance of 4 meters and you double it to 8 meters. What happens to your dose? So something like that. They just want you to know the principle behind it, okay? What happens if you half your dose, or you half your distance? Increase your dose by a factor of 4. Okay, so if you half your distance, you increase your dose by a factor of 4. So remember this when you're a tech and you're actually close to the fluoro unit, if you back up, doubling your distance, you're decreasing your dose by 4 times. This is useful for you, right? We don't know all of the harmful effects of radiation. You don't have to be scared about it, but you can be smart about it and reduce your dose by backing up. All right, fundamental properties, we went over that. X-rays travel in straight lines, ionized matter. We have a nice presentation on it somewhere under here. We're gonna hang it up on the board. Any questions about that? The 12 fundamental properties of X-ray. Okay, I think we're good. There. Don't get confused by thinking about X-rays and a sinusoidal wave. I've had students think about that before. They get confused, how can X-rays travel in straight lines if it's a wave? Because we have a wave that's moving. It's still traveling in a straight direction, even though it is a sinusoidal wave. So don't get confused with that. X-rays travel in straight lines. All right, photon interactions with matter. Did we go over photoelectric? Did somebody go over photoelectric today?
Yeah, we went over it.
We did. Do we need to go over it? Yes. Okay, somebody explain it to me. Somebody explain to me what photoelectric interaction is.
Electron comes
So isn't an electron coming in?
No.
Good, it's a photon. Good. So this is how we distinguish it. So it's a photon entering, what happens?
It knocks out the K-shell.
Good, knocks out the K-shell. Electron, good. What happens?
Photon is positive.
Good. And then we have a cascade effect, right? So just the same as characteristic, except the initial introduction is an incident photon, not an incident electron. We have total absorption of the X-ray photon, and this is how we actually have an image.
And the energy has to be higher than 69.
Good, the energy of the incoming photon must be higher than 69.5 because we have a K-shell interaction. Very good. So we can estimate it to 70 kbp.
And how are we getting images that are like 50 kbp?
How are we getting images that are using 50 kbp? Okay, through the process of photoelectric effect, but it's minimal. You're saying, how do we have it if we are not using 70 kbp? Because we have different interactions with matter. How do we have an image if we don't use at least 70 kbp? That's a good question. How do we have an image if we don't use 70 kbp for a hand?
You're still using it.
So we're still using NAS, good. But as far, we already have X-rays produced, right? So we already have the production of X-ray at the target. So traveling through, even though we don't have photoelectric interaction every time, we do have the X-rays that are produced already. We have remnant radiation going onto the image receptor. That's how we have an image. Good question, I like it. Okay, Compton, do we want to talk about it? No.
Strikes a loosely bound outer shell electron.
Loosely bound outer shell electron is probably going to be your key. Loosely bound outer shell electron. We know that this is the contributing dose factor for occupational workers like us, right? Scatter, because it's going to scatter off of the patient or scatter off of the image receptor onto us. So it's going to increase our dose. It is harmful X-rays, non-diagnostic. So scatter normally doesn't help attenuate an actual image. It just contributes to fog. Or extra or entrant skin exposure dose. Okay, what about classic incoherent? Ashley told us about that. Do we have questions about it? Do we feel good? Low energy is what you want to associate that with. We don't use this in X-ray, right? Only low energy. And then attenuation by various body parts. So what do we have written down for this one? Attenuation by various body parts, thickness of body part, and type of tissue, aka atomic number.
Thickness of body part increases the attenuation. So
Good.
you have larger part, more attenuation.
Good.
More absorption.
Good. If you have a larger part or a thicker part or a higher atomic number, you have more attenuation because you're able to stop the beam more. Okay. So anything that comes between, I always think about this projector as my X-ray tube. If you guys wonder why I come to the center of the room, I always think about the board as my image receptor and this projector is the X-ray tube. So I'm standing right in front of it. The thicker body parts or the higher atomic numbers, meaning metals. If I had my cell phone, it's going to attenuate more than this water bottle, right? We would push through this pretty easy, but any reduction of beam, so any reduction of beam is gonna be encompassing of attenuation. And then what about types of tissue or atomic number? Do we have anything written down for that?
The denser the
directly
tissue,
correlated.
more X-rays are attenuated.
Good, so it's a direct relationship. As the atomic number tissue increases, the attenuation increases. Because we have more absorption, meaning we have more reduction of beam intensity. What are we talking about here?
SI unit.
SI units. All right, so what does NCRP stand for? Good, National Council for Radiation Protection. If you didn't know that, it's listed on document 160. If you'd like to Google that and look at this information. Do we have anything else for, just in general, SI units of measurement? Or did you guys just go straight into breaking them down? That's probably what I would have done.
We don't need to know the traditional, you said?
We don't need to know the traditional. You do not need to know the traditional. That's why I'm giving you credit for that one question. But I didn't write it down yet. So, number 100. Credit. All right, anything else we want? Okay, let's break it down. Absorbed dose. So what do we have written for absorbed dose?
Determines the amount of energy from the X-ray beam that is transformed to the absorbing object.
Okay, so it's like our general dose. Can be abbreviated by a capital D. Remember we talked about that. Dose can be summarized or abbreviated by capital D, absorbed dose, and it's measured in what unit? Gray, good, which is capital G, lowercase y. Do not memorize any of the information if you're using the Kettering on the conversion of traditional units to gray. That's all you need to know. Any questions on absorbed dose? This is like our basic dose.
I have here, there's a general rule of that the absorbed dose is proportional to the degree of beam attenuation.
Okay, sure. Yes, if you attenuate more, you have more dose. If you attenuate more, you have more dose. I like it. All right, what about dose equivalent? What do you guys have for this one? Obviously, it's measured in sievert.
Product of,
It measures biological radiation.
Effectiveness?
times
Good.
radiation weighted factor.
Good. So measurement of the biological effectiveness of radiation, and it uses the weighting factor. The weighting factor.
Radiation protection.
Is the measurement of occupational exposure.
Good. Radiation protection occupational dose. This is usually what we document our dose in. Sieverts or dose equivalent. Sieverts or dose equivalent. Takes into account the biological response of the actual radiation. And what about the quality factors for these? Do you guys have these written down in your section? Okay, I would for sure know X-ray, gamma, alpha, and protons. I would know those for sure. So X-ray and gamma are the same quality factor, and then we have protons, which are 5, and then alpha particles, which are 20. I would definitely know those for your registration. Is it 2 in our book? In our radiation protection book? Ooh.
What is that?
What does it say? Does it say fast-moving neutrons or protons, or what does it say?
It just says
Does anybody have a radiation protection book?
I do.
For protons, it says 2, for neutrons, it says 5, depending on the.
Well, I have the old one.
What is, I have
The old one, that's the work one.
I don't know which You have the older one? Okay, let me check the number and I'll get back to you guys. What's the discrepancy? Protons?
Yes.
Weighting factor of protons.
2 or 5.
Kettering has 5. Somebody's saying our radiation protection book has 2.
Yeah,
And
because
the
it
prep
says
says
2.
alpha.
Okay. 2 or 5?
Alpha's 20?
Yes.
Yeah.
Yes, alpha's 20. Alpha is 20 standard. I do know that one for sure. Do you know how to calculate this? Do you know how to calculate this?
Gray times quality factor.
Gray times the quality factor is going to equal the Sievert. Gray times the quality factor is going to equal the Sievert. So your dose times the quality factor is going to equal the Sievert. I will check on the proton quality factor though, because that could be confusing. So why is it that gamma and X-rays have the same quality factor? How do we distinguish these two?
The LET.
Okay, the LET is going to be the same, but how do we distinguish the two?
Is the concentration of the X-rays are more like spread out, whereas the other one is more like a concentrated.
Good, so she's saying it's like condensed or compiled together, but what you want to remember for your registry is the origin. The origin of X-rays and gamma is different, the origin. So the actual weighting factor is the same because they interact very similarly. But the origin, how is gamma made? Pair production, good, which is nucleonic decay. So it's made by some kind of decay, right? So some kind of combustion, something explodes, and you have a gamma ray released. We know how X-rays are created or produced. We already went into all of those details, right? Fast-moving electrons, decelerization.
What is it that you said, the something decay,
Radioactive decay, yep. Combustion, so the actual explosion. What is
What's
it?
the number for those two?
1. The quality factor for X-ray and gamma is 1. I would for sure know that. They like to ask the question about how do they differ? How do X-rays and gamma rays differ? The origin, so how they're made. As far as physics is concerned, they're pretty similar in the way they react and interact with the body and the tissue, but the origin is completely different. We make X-rays with fast-moving electrons. Gamma rays are made by radioactive decay or combustion. Good. Okay, so the next one is going to be exposure, which we measure in what? Coulombs per kilogram. Good. Exposure. Coulombs per kilogram. Coulombs per kilogram. And what is exposure?
Unit of radiation.
Number of ionizations in the air.
Number of ionizations in the air. Number of ionizations in the air. Number of ionizations in the air. Number of ionizations in the air. Exposure. So we're not talking tissue at all. Number of ionizations in the air. Right, so not a good measurement to compare tissue dose, but we do use this one. And then what about effective dose?
The risk presents when various tissues are aerated.
Good. So now we're bringing in a tissue weighting factor, right? So this is our most responsive dose. We like this one the best as far as tissue is concerned, just tissue being concerned. And then our dose equivalent, how they kind of worded it in here in the actual test specifications, they put in first here. Dose equivalent is using type of radiation and tissue, whereas we have effective dose using only tissue, using only a tissue weighting factor. You guys are starting to look dead on me. You guys are starting to die and decay in here. I sense some radioactive decay. All right, what about air kerma?
Define radiation exposure or radiation delivery.
Good. Somebody else said it. Kinetic energy released in matter. So KERMA is an acronym. Kinetic energy released in matter. Do we need to know anything else about air KERMA? What's the measurement? How is it measured? Great. Good. Good. Anything else?
How's that different than exposure?
Good. How is it different than exposure? Because it's released in matter.
Exposure to the air.
Yes.
Air is matter.
Matter being tissue. Good. Think about matter associated with tissue. So air KERMA or KERMA is a more specific dose specifically to matter. So some kind of tissue, bone, high atomic number. Whereas exposure is specifically to air. Air KERMA is a newer one. So we're learning more, we're increasing our sensitivities there. Okay, how about radiosensitivity? And then we have dose-response relationships. Dose-response relationships. So this is where we talk about threshold and non-threshold. Threshold and non-threshold. So tell me the difference.
Non-threshold is if there's no amount of radiation that is safe
Good.
the body.
Non-threshold, no amount of radiation is considered safe.
And
And
for
there's
threshold,
zero
there is
effect.
there is some kind of amount that affects the body. It
Good.
will produce some kind of a damage to them.
Threshold, so how you would recognize these on a dose curve.
For not threshold, it's starting where it interacts X with Y, so there's 0. And it has some kind of amount of X.
Good, good. Okay, so non-threshold, if they gave you a question on the registry, would look something like this. Because there is no threshold, meaning it starts at the X and Y axis, intersecting there, no amount of radiation is considered safe. If you get any kind of a dose, there is some kind of likelihood that you might have a response to it. We don't know what it is, there is no threshold. Threshold says once you receive, I don't know, 5 milligray, you are going to start presenting with signs of cataracts. Okay, so there's a limit. There's a limit or a threshold. So when they say dose response curves, this is something that they could give you. This is a relationship. So the dose is gonna be the x-axis, the y-axis is going to be what? Tissue irradiated. Tissue irradiated. How do we feel about those? Threshold and non-threshold responses.
I like the graph helps,
Okay.
because it's hard to kind of like understand. from the graph.
You don't need to go into detail. Kettering goes into linear, curvilinear, or sigmoid curves. You do not need to go this deep if you have the Kettering study. So I would know threshold and non-threshold. Threshold and non-threshold. Non-threshold, no amount of radiation is considered safe. Threshold, you have to receive this amount before you start presenting symptoms of it. Okay? Okay, and then we have relative tissue radiosensitivity. So we have LET and RBE, which Jenny covered. Do we have questions on these still? Let's talk about just a little bit. What is LET?
Greater than deposited per unit track linear.
Good, so the rate of energy deposited per unit track length through an absorber. And then what is the difference between RBE and LET? What is RBE? So biological damage. So we know that as we increase the energy transfer, so as we increase the LET, we're gonna also increase the RBE, which is the relative biological effectiveness. So damage to the body.
Is
What?
directly affected to the RBE.
Yes, they are directly related, exactly. They are directly related. One is talking about the energy being transferred, and one is talking about biological damage. So RBE, biological damage, actual tissue response. LET, how well is the radiation able to transfer energy? And we know when you transfer energy, you produce a response, which is damage to the tissue or DNA. Breaking it down, kind of easy for you guys. And then in the middle here, I have the oxygen effect. I know it's different on this actual test specifications, but we're gonna skip cell survival and recovery and go into oxygen effect because it has specifically to do with the LET, so that's why it has it listed like this. What is the oxygen enhancement effect?
The cells that are more oxygenated, they have a larger chances to get damaged.
Good, so as we increase the oxygen, we do what to the damage? It doesn't have to do with the octet, because we're talking about oxygen being present.
It increases the cell sensitivity to radiation.
It increases the cell sensitivity to radiation, exactly. So if a cell is alive, if there's oxygen present, we have more damage that can be taken place to it. So increasing the oxygen, aerobic conditions enhance the effectiveness of radiation. So as we irradiate tissue, if there's oxygen present, we can have more damage than if we take away the oxygen. Lines, pretty simple there. And then what about the oxygen enhancement ratio?
Just a numeric description.
Just a numeric description. And I think I gave you guys the OER in Rad Bio when we covered it of human tissue is 3. 3. So the OER for human tissue has a maximum of approximately 3. And that's just the numeric description of oxygen being present in the body, increasing the radiosensitivity.
But we're not gonna need to know the numeric description for the, like the actual equation.
Well, you won't need to know the actual equation now. You won't need to know the actual equation. But the OER is the equation, so know that it is the numeric description of the oxygen effect. You can use the OER to determine how radiosensitive the cell is when oxygen is present. We won't actually have to compute that though. Not our job, right? Okay, so let's back it up just a little bit and go to cell survival and recovery, and then we have LD50. So cell survival and recovery and LD50. So what do you guys have for this?
As LET increases, the probability of cell survival and recovery decreases.
As LET increases, the what?
Probability of a cell survival and recovery decreases.
Good. So as we increase the LET, so the linear energy transfer, we decrease the likelihood of the cell being able to recover or live. Good, good. What else do we have about cell survival and recovery and then LD50? What is LD50? Okay, so what does that mean?
50% will die in 30 days.
50% of the population
Dies in 30 days.
and dies in 30 days. Good. Dies in 30 days. May die in 30 days, right? And then what about recovery? I know it's not really listed in this breakdown, but I know we talked about it more in Rad Bio. So as far as cell recovery goes, we have the target theory. Is the target theory on here?
The single rung on the ladder is broke, it can probably heal. If it's a double break, then it's probably not gonna heal.
Good. So the more rungs or more ladders that we strike with the radiation, the less likely the cell is going to recover or the DNA is gonna recover. The more likely, the more rungs that are strung or the more rungs that are struck by X-ray, the more likelihood we would have mutation present as well. So when we start talking about DNA, we start talking about generational mutation, things like that. And what about the target theory? Do you guys remember that one?
If the vital piece of DNA in the cell center is destroyed, then there's a chance of the cell dying.
Good, the master molecule, which is DNA. So if we strike the DNA, specifically, the cell will die because it won't know what it's doing. So the target theory is kind of encompassed with that, the master molecule there. Let's see, anything else we want to talk about with cell survival and recovery? Do we feel good about those? Cell survival and recovery, does anybody else have anything else? No? Yes?
I put, long-term retina effects not observable for 5 to 30 years, cataracts, infertility, and organ failure.
Okay. Okay. I like that. All right, let's move on to somatic effects. Somatic effects. So somatic effects being what?
The person that was exposed.
Good. Soma, tissue, body. Somatic effects, soma, tissue, body, associated with it like that. Cells and tissue. So what do you guys have for cells?
It can either replicate or not replicate, it can continue to function but not replicate.
Good. So coming back to the Rad Bio days, So you could either be able to replicate still, you can have a struggle replicating, you could not be functioning at all, or you could die, depending on the type of actual interaction that's occurring to the
It
cell.
also depends on maturity of the cell.
Correct, which is the law of,
Good.
good, Trippin-Doe inversion A, which states,
Metabolism of the cell is directly correlated to its
radiosensitivity. Good. Metabolism of the cell is directly related to the radiosensitivity. So as a cell matures, it is less radiosensitive. Good, good, good. Anything else with that? Cells, tissue. So tissue, and then it has eye, thyroid, breast, skin, marrow, and gonad. What do you guys have for somatic effects tissue? So 3B. Somatic effects tissue 3B. Do you guys have these written down?
The hematopoietic system, bone marrow, lymphatic, reproductive.
So he's talking,
gastrointestinal, and then mucus.
okay, so he's talking acute radiation syndromes, which would be under H. So 1, 2, and 3, hematopoietic, GI, and CNS. Let's talk about specifically, let's break these up. This book has it actually.
And the tissue reading
has it broken down really nicely here.
So the eye, like it, I put down like you can get, radiation cataract.
Right.
Posterior pole of the lens, non-linear threshold dose.
Good, so follows a non-linear threshold dose. Non-linear, meaning it's not a line, and then it has a threshold dose. So that means that they know that there is a threshold for cataracts, right?
There is some kind of exposure that will produce it.
Yes, there is an amount of exposure that we know for sure you will get cataracts if you get this amount of dose now. So it is a threshold dose. Okay, what about thyroid? Because they mentioned that as well.
Linear, non-threshold.
Linear, non-threshold. Linear, non-threshold, which means what? It's a line, and then non-threshold means what?
Any exposure.
Any exposure, stochastic, meaning we do not know what affects it. We do not know what affects it. I would definitely write these down if you guys don't have these relationships down.
You said the eyes are non-linear threshold, and
Non-linear.
thyroid is linear.
Linear, non-threshold.
Linear.
Linear, non-threshold. Alright, and then let's go into breast. Linear, non-threshold, because we don't know the dose, but we do know as the dose increases consistently, it increases our response or biological damage. What about skin?
Arrhythmia, alopecia.
Good, arrhythmia for skin, which means what? Reddening of the skin. This was our first dose. Remember we talked about in rad bio. So initially, if we didn't have that radiodermatitis or any kind of reddening of the skin, they didn't think that anything was going on, when really it was deep within the body.
The threshold dose.
It is a threshold dose. Good, it is a threshold dose, meaning what?
Reason not for
Good. Alright, and then the last one we have on here, oh, I'm sorry, we have marrow and then gonad as well. So let's talk about marrow, bone marrow. What do you guys have written?
Reduction of red and white blood cells.
There might be a reduction of red and white cells and platelets. So a reduction of these, and it follows a linear threshold response, a linear threshold. So once you receive this amount of radiation, you can have some kind of bone marrow instance occurring. Okay, and then for real, the last one this time is gonad. Gonad, what do we have for gonad?
Female and male.
Good?
Female, you can destroy new or mature ova, genetic damage can be passed down.
Good, genetic damage being passed down because we're damaging radiosensitive immature cells. And then what do we have written for men?
For receivers and permanent.
5 to 6 grays can
Permanently
cause
sterilize
damage. It's permanent or sterilized.
5 to 6 grays can permanently sterilize them. What did you say?
4 sieverts.
4 sieverts. 4 sieverts or 5 to 6 grays. Okay, that's correct. Alright, so you could write it either way. 5 to 6 grays or
4 sieverts.
4 sieverts sterilization of males. And then, let's see, skipping down to embryo and fetus.
First trimester is the most radiosensitive.
Good, we know this as the 10-day rule, right? So the 10-day rule you might see on the exam, if a person has not menstruated within 10 days, we want to pregnancy test them if they're not sure if they're pregnant or not. The first trimester cells are the most radiosensitivity, or have the most radiosensitivity, or are the most radiosensitive because they contain those stem cells that don't know what they're gonna be yet, okay? So they're just hanging out in the body, waiting to explore, waiting to figure out what they are going to be. So they are extremely radiosensitive.
The relative risk of developing childhood leukemia following radiation in utero increases in the second trimester.
Increases in the second trimester. The relative risk of a childhood developing childhood leukemia, radiation increases in the second trimester. I don't think we need to know anything specifically about leukemia, so if you do have that written down in your,
It was out of the category.
in your catering or in your study guide, for first or second trimester leukemia relations. I don't think we need to know those. Anything else regarding embryo or fetus? How about radiation protection, since this is the radiation protection and safety section? Always shield children when you can, use the lowest dose possible, use the lowest mass possible, use the shortest exposure time to prohibit motion and repetitive exposures, and never x-ray pregnant women, right? Never, always ask, and 10-day rule. If they aren't sure if they're pregnant or not and they have not menstruated within 10 days, you have to pregnancy test them, because those fetal cells within the first trimester are extremely radiosensitive.
Do you have a different dose limit if you're a pregnant radiographer, right?
You do have a different dose limit, yes. You do have a different dose limit, and I think the dose limits are covered in the next section. Maybe. They're either, yes, they are. They're covered in section 2BB. So we'll talk about them next class. We are actually gonna talk about the dose limits. Okay, carcinogenesis, what is this one? What do we have down for this one?
Cancer formation after exposure.
Cancer formation long after an exposure. So these people who had some kind of large, massive radiation event, some kind of atomic bomb, radiation, nuclear power plant exposure, carcinogenesis, cancer formation long after a prior radiation exposure.
Can also be caused by viruses, retroviruses.
Say it again, I'm sorry.
Said it can also be caused by viruses.
Can also be caused by viruses. Interesting. What kind of viruses?
Retroviruses.
Retroviruses. Oh, okay, like SARS or COVID. Okay,
Destroys your DNA.
I like it. All right, early versus late or acute versus chronic in somatic effects. Early versus late or chronic versus somatic. What do we have written down?
Early is loss of appetite, nausea, vomiting.
Good,
And late, cancer and cataracts.
good. Anything else that we have written for these?
Fatigue, skin changes.
For early or late?
Early.
Early, fatigue and skin changes. Did you guys find these? Okay, they should have been in your radiation protection book. Questions on these early or late reactions?
Hair loss and mouth problems.
Good, I would definitely be able to distinguish these on a registry question. They might say which one of these is an early effect versus which one of these is a late stage effect. Know that if it's any kind of carcinogenesis or cancer, it's going to be a late effect. We're not gonna wake up tomorrow after radiation exposure and have cancer. It's gonna be years to come. What is the difference? How do we distinguish early versus late? What's the time frame?
For short term, it's, early hours, days.
Good.
weeks, minutes.
Hours, days, minutes? And then what about for long or late reactions?
Years.
Months or years? Good. Good. Okay, then we have deterministic or tissue reactions versus stochastic. What do we have written down for this? This can get tricky.
Deterministic cause and effect relationship between ionizing radiation and certain side effects.
Good. So deterministic, you could relate to what? A threshold or a non-threshold?
Threshold.
Good. Deterministic effect you could associate with a threshold dose response curve, meaning you have to get this much radiation exposure to have the effect.
The biological effects increase in frequency and magnitude.
Good, they increase in frequency and in magnitude, meaning it can expand the number or the amount of disease you have and how severe it is, meaning the magnitude. Good. Anything else on that one, deterministic? What about stochastic?
It's a non-threshold.
Good, stochastic is a non-threshold. So-
Probability of biological occurrence rather than severity of effects. Magnitude does not increase with increasing dose.
Right, so stochastic, we could relate to this one. Versus deterministic. Non-threshold versus threshold response. And then we have short-term versus long-term exposure. Short-term versus long-term exposure. This is worded interestingly. What do you guys have for this one? Short-term versus long-term exposure under somatic effects.
Short term after a large dose, and long term is after several doses over a period of time.
Like fractionated or protractinated, is that what they're trying to say? What, is that what you guys have down?
Long-term effects are those
Isn't
that
it
occur
kinda like-
years after exposure.
Long-term effects are those that occur years after exposure.
Yeah.
All right, short-term, you have what? Long-term exposure effects. I don't really know how they're writing this.
Hair loss, hearing loss, memory loss, things like that.
It can, occur soon after the exposure.
Is it kinda like early and late?
I think they're just
Yeah.
categorizing it early and late, short-term and long-term. I think it's synonymous. So if you want to rewrite what you wrote for early and late versus short-term or long-term, I believe it's the same thing.
Well, cause like for the, like the acute and chronic, basically. So chronic, like we put, or I put, delivered in small increments over a long period of time, and then acute large dose over a short period of time. So I feel like they're like,
Versus long-term exposure. Okay, so let's break it down in this category. Is it better to, I think it's talking about fractionated and protractinated here.
That's what it says.
I do think so. Is this in the Kettering book?
Long-term
Chronic-
protract.
chronic is protraction.
Do you guys have these terms written down? Or are you guys lost?
It's earlier in the Kettering book.
It's earlier, okay. Now I wanna see what they say about this one, because this is a newer section. Fractionation versus protraction in a single dose. Okay. So I do want you to write these two terms down because I do think they're registry eligible under this section. So fractionation is equal doses of radiation that are delivered within interval time separations. So fractionation, equal doses of radiation that are delivered within time interval separations. So this is somebody, picture somebody coming in and receiving radiation therapy. So they're coming in a bunch of different times, but they're going to receive the same dose.
One more time.
Okay, fractionation, equal doses of radiation that are delivered within timely interval separations. So we're separating the time out, but giving the same amount of dose every time.
So like chemotherapy?
So we're talking about radiation.
Friday, we're getting fractionated.
Right, so we're fractioning out the dose, the same dose every time. So think about radiation therapy, think about somebody who has to go in several times a week. They're receiving the same amount of dose over a period of time. Then we have protraction. This is our other term here, protraction. This is a radiation dose that is delivered continuously, but at a lower dose rate. Continuously, but at a lower dose rate. So meaning you come in for an hour and a half and receive a very low dose of radiation, but it's a longer period of time. So the benefit is fractionation offers a cell the greatest ability to survive and recover from the radiation.
Can you say that first part one more time?
Good, protraction?
Yeah.
Protraction, radiation dose that is delivered continuously, but at a lower dose rate.
So which one is,
So it's
short
chronic,
and long?
protraction, and acute,
Acute would be fractionated, yes,
yeah.
yes. If you wanted to break it down, acute versus
So
chronic.
fractionated would be short,
Fractionated is the short doses every day. Short doses every day. Or over a period of time. Whereas you have protraction, which is a radiation dose that is continually given in one time period, but at a lower dose. So you come in on a Tuesday, you receive 2 hours of radiation at 4 gray, versus you coming in Monday, Wednesday, and Friday and receiving that same amount of time broken into smaller sections. Broken down into different sections. The reason why they talk about this under radiation protection is because they want you to know if you deliver smaller doses of radiation over a longer period of time, your cells are more likely to recover versus you receiving one large, long dose. There's two different types that you could deliver this in.
That would be under protraction.
Yeah. So fractionation versus protraction, the different ways we could administer radiation. This is specific to radiation therapy, so I'm not sure that you would get a question on this, but it does say short-term exposure versus long-term exposure, and I think that's what they're talking about here. This is a new section that we're adding in this year, so this was not on the prior years. So fractionation offers the cell the greatest ability to survive and recover, rather than one long dose. So if you give them a little bit of radiation today, let them leave, go home, recover on Tuesday, they come back on Wednesday, the cell is more likely to survive. The cell is more likely to survive. Okay, and then we have our ARSs, our acute radiation syndrome. So we have hematopoietic, GI, and CNS. So what do we have for hematopoietic?
Actually, bone marrow syndrome.
Good, bone marrow syndrome.
Decreases
Doses
the
are
number of
between
white
1 and
blood
10.
cells.
Doses are between 1 and 10 gray or milligray?
Great, whole body.
Gray, whole body, good. And then what else do we have for that one?
It
Can result
also
in
suppress
death.
the immune system.
Affects-
Body mobility.
Affects the immune system, is that what you said?
And death can occur between 3 and 6 weeks after exposure.
Good, 3 to 6 weeks after or following the exposure.
And actually, the lymphatic system is the most sensitive, radiosensitive system in the body.
So the hematopoietic system is the most radiosensitive system in the body. Why? Because we're constantly regenerating our blood. So think about it, our bone marrow right now is regenerating our red blood cells. We're pushing blood throughout our body, so we have immature and mature cells in our body. That's why it is the most radiosensitive. Let's talk about the other one, GI, the GI syndrome.
So obstruction of the GI tract can result in death.
Good. Nausea, vomiting, fatigue. Nausea, vomiting, fatigue,
Doses
great.
between 10 and 50.
10 and 50 gray is the required dose for this one.
And death can occur 1 week after the exposure.
Death the following 1 week. Here. All right, CNS is our last one, central nervous system.
You said nausea, vomiting, and what?
Fatigue.
Oh, fatigue.
Yep, nausea, vomiting, and fatigue. So CNS, they also note this one as cardiovascular syndrome, and it occurs with an exposure of 50 gray. Exposure or death could occur within days or hours. And what else do we have for CNS? Do we have some symptoms?
I have convulsion and coma.
Convulsion and coma. Good. So anything related to the CNS. I like convulsion and coma. Do we have anything else written down for that section?
So it's normally the least radiosensitive, but when you're hit with that much radiation, it's the quickest to shut down.
Good. So CNS is usually typically the least radiosensitive because these cells are the most developed and the most mature, the most specialized. But when you are hit with that amount of radiation, 50 gray, death is going to occur within hours. Good. How do you guys feel?
Tired.
Everything's done and tired. Better than last month. Okay, do you feel like you're getting stronger?
Yeah.
Yeah, this is needed. All right. So next Wednesday when you come in, we don't have an exam next Wednesday, right? I don't have the schedule in front of me. All right. Next Wednesday, we are gonna go over the second section of RAD safety, so make sure you come prepared with that. I will check it before we start next time. And then make sure you are prepared with your presentations. Hopefully, building on this is going to increase your mock registry scores. Somebody asked me, how do I study for your mock registries? I wouldn't study for them. I would go through your study guide and do your test specifications. Okay, that is going to increase your scores. All right?
You're gonna post the correct answers?
I'm going to post the correct answers, and if you want to do the extra credit, remember it's up to 10 questions, 10 points of extra credit, and it's due next exam day.
And are we gonna post that on campus or?
You're gonna post it on campus.
Okay.
Yep.
Can it be written or typed?
It can be written or typed, and if you have questions specifically regarding the mock registry that I gave, email me, and I'll make a post about it. Okay?